Today we're going to learn about QG energetics. And so we've looked at three other lenses for mid-latitude cyclones in the atmosphere. We looked at our traditional QG dynamics. We've now looked at our isentropic view and our PV view. And today we're going to focus a little bit more on a topic we've kind of skirted around a couple of times this semester, and it's this idea of QG energetics. And so the atmosphere can really be described as a stable heat engine. And so really what we're talking about then is we're talking about energy moving around in the atmosphere, right? We can either create or destroy energy. And so one of the questions is, how do we then identify these energies, and how do we identify kind of when they get going? And so really what we're talking about here are some local instabilities. And so we've got two primary local instabilities that we consider in the atmosphere that we actually talk about quite a bit, but we don't always talk about in this energy framework. And one is our baroclinic instability. And the other is our barotropic. And so our baroclinic instability has to do with temperature gradients and density differences that we can realize some available potential energy. And barotropic is due to instabilities within the flow itself. And so ultimately what we want to be able to do is to describe ways in which this energy can move around in our atmosphere. And ultimately, the atmosphere's goal is to restore balance. And imbalances are generated by the atmosphere, and then that leads to the buildup of available potential energy to then be realized in kinetic energy. And so imbalances lead to available potential energy, APE, which then gets used up through our kinetic energy, primarily in the atmosphere, our wind. So the question is, well, what amount in the atmosphere might be available for use in conversion to kinetic energy? And so let's do a little thought experiment to then tease out this idea of the difference between our total potential energy that the atmosphere might have, which can be quite a bit, versus then what is the small amount that is actually available for use to drive then our weather systems. And so we're going to do this by thinking about a kind of basin that we've got filled with water, and that on one side of our basin, we're going to have cold water, which is indicated by our little blue dots here, and then on the other side, warmer water, at least in a relative sense. In this situation, we can define the center of mass here to be exactly in the middle, since we have all of our water on either side, that the center of these masses for these columns is going to be right smack dab in the middle. And so we have our height here of the center of mass initially as Zi. And so this is at time t equals t naught, when we haven't done anything yet. And so the question we have to ask ourselves is, we know there's a certain amount of potential energy here, right, related to this idea of the center of mass. We go back to our physics principles. And so if we were to remove our barrier, this magenta line, intuitively, what do we know should happen to the water? That's right. We know that this cold water is going to be denser, and so therefore it's going to sink towards the bottom and then push towards the right of this image. And so let's go ahead and draw that next tub after we've removed our barrier. So now we're at T naught plus some delta T. And knowing that this cold air is going to move, we know that we're going to get at some intermediate time some sort of kind of distributed surface with the cold air kind of sinking towards our bottom, which we can indicate here with an arrow. So we know that some of that cold air is going to shove towards the bottom because it's denser. And then we also know it's going to shove to the side because when we remove that barrier, we've got less dense air to our right, which is then going to push up our warmer water. And then we essentially are going to create a circulation. This shouldn't be too surprising. As this is just a common thought experiment, and we've taken some initial thing that has some amount of potential energy available, and we're beginning to use that and create a flow, which is our kinetic energy. And so our flow here is our KE. And so as we go through time then, and if we let this settle out completely, we need to ask ourselves, well, what's going to happen to our system? And so if we do so for a long period of time, we know we had equal amounts of cold water and warm water. So we know that our cold water should end up at the level of our original center of mass. And now all the cold air is going to be, or the cold water in this case, is going to be on the bottom. But the question is, what has happened to our center of mass? Our center of mass, now since we have all of our denser material on the bottom, is going to be reduced. And so now, the height of our center of mass is at this Z final level. And so, the only amount of available energy that we've used is this little amount there. This was, in fact, our available potential energy in our system that we were able to use and convert to our kinetic energy. It's a very little amount. Otherwise, we still have the rest of this potential energy as our center of mass is not completely at the bottom of our tank, nor will it ever be. Just as in the atmosphere, we can never realize the full potential energy of the atmosphere. We can only realize these small amounts, this available potential energy that is available at any given time. One thing to recall here, right? We know of a very common available potential energy that we've used quite frequently throughout our career so far, and that is CAPE, right? Convectively available potential energy. And so there's all different types of available potential energy, and the one we're talking about here today is those that are available to our synoptic scale systems. And so on any given day, the full potential energy of any given column is 2,000 times that of the kinetic energy produced. And that's because we only have such a small little amount that is available for use on any given day. Another thought experiment that we could think about in terms of this difference between what's available versus the total potential energy is if we held a book over a table. If we were to then release that book and it were to fall to the table, right, it would be using up its available potential energy and its kinetic energy during its fall. Now imagine that instead of over the table, we had the book hovering over the floor. We have now increased its available potential energy, and that the amount of kinetic energy used would be greater as it traveled all the way to the floor instead of just the table, but that we've never used up its full potential energy, which would be the energy towards the center of mass of Earth, because we just can't reach that center of mass. And so we only have those small bits available to us. But that depending on our frame of reference, whether it's the table, whether it's the floor, whether it's the ground outside, will determine the different amount of available potential energy that could be then available for conversion to our kinetic energy, thus creating motion in that system. And so we can think of this similarly in the atmosphere in terms of our kinetic energy. And so we want to define here our idea of kinetic energy, Ke, as equal to 1/2 mv squared, which is our classical definition of kinetic energy. But in the atmosphere, we often like to do things per unit mass. So we could say that we have a certain amount of kinetic energy per unit mass. For example, CAPE, right? those units are joules per kilogram, energy per unit mass, such that we end up with a simplified equation of 1/2 v squared. Now again, in the atmosphere, we don't necessarily need to know the total wind. We want to know just what is different than average, because that's going to be more aligned with the kinetic energy that then is available, or that would be available from the potential energy to be used. And so we can think about things in terms of a perturbed state. And so a perturbed state, let's recall that we can define any variable a as a bar plus a prime. A bar is our average state, and a prime here is our perturbed state. And so we could solve for the perturbed state, a prime as equal to a minus a bar. And so this perturbed state is going to help us to define the kinetic energy equation that might be most useful for us in synoptic meteorology. And so then going ahead and writing our kinetic energy with respect to our geostrophic wind, we can define that as UG prime plus VG prime quantity squared over 2. And so we can define the kinetic energy at any given time. Pretty easy calculation to do. Subtract the average state from our U and G variables, square them. And I wrote this equation wrong. Each one of these should be squared, not our overall equation there. Right? Each component squared divided by 2. And that's great, and we can define that, but really what we care about in the atmosphere, right, we're forecasting things. How are things changing in time? And so we can actually rewrite our equation as the time rate of change according to our geostrophic flow of this quantity UG prime squared plus VG prime squared all over 2. And we end up with 3 terms on the right-hand side. And so the first term can be written as minus del dot the quantity phi prime, so our perturbed state, times the ageostrophic wind vector. Our second term, minus RD over G times P times omega prime T prime. And our third term, minus UG prime VG prime dUg bar dP. Now this first term should look relatively familiar to you. This is our ageostrophic geopotential flux term, right? This is downstream baroclinic development term, right? Energy flow through our wave pattern. This second term is a statement of baroclinic conversion. So basically using our baroclinic instability. And our last term here is our barotropic conversion. And so the way we can tell these two apart, baroclinic, darn spelling today, is that we have that omega prime in there, right? Related to, and T primes are related to temperature gradients and rising motion as a result of it. So to some extent, what we're seeing here is the ramifications of temperature advections. In our barotropic term here, right, we have the shear of the geostrophic wind going on. And from there, right, it's just changes in U values, right? So just changes within the flow itself, which lends itself to be a barotropic conversion term. In a future video, we're going to go ahead and look at these 3 terms in particular and how they manifest in creating from available potential energy within these terms to the kinetic energy that we're describing within this term. Thanks for watching.